In this video, we'll go through how to create our own FIR filters and implement them using the CMSIS DSP libraries on a custom embedded system using an STM32 processor. What you're currently seeing here is the left PCB, which is a digital signal processing PCB that's featured a few times on this channel. Essentially, it's a single input, single output digital guitar effects processor. At the center of this is an STM32 microcontroller. We have an audio codec, so DACs and ADCs, and analog front ends. And this is just running in mono with USB connections and connections to ADCs for example, peripheral controls such as potentiometers, switches, and so on. I'd like to use this as a demonstration platform along with the CMSIS DSP libraries to show you how we can do real-time FIR filters. In essence, those are just convolutions, and we can test the input-output behavior, for example, in the frequency domain using an audio analyzer such as the Quantasylum QA43 running on the right-hand side. Being able to implement FIR filters is incredibly useful because we can have very, very tailored frequency responses or filter responses. For example, the filter that I'm running here is an FIR filter where I've defined various pass bands with various gains, as well as various stop bands with various stop band attenuations. And these FIR filters compared to IIR filters are comparatively very precise in the frequency bands they can attenuate, amplify, and so on. They don't suffer the same stability issues, but they do come at a price that they are rather expensive to compute. We are essentially computing convolutions, and doing this in real time, for example, in an audio system, can be quite time and computing intensive, even on these STM32 microcontrollers. Therefore, in this video, I'd like to show you how to implement this FIR filter in C using the CMSIS libraries, which are optimized for these ARM microcontrollers and faster typically than writing our own algorithms. If you haven't already, or if you're new to FIR filters, I'd strongly suggest watching video number 17 on my channel, which goes through the basics of FIR filters, the theory behind them, including convolution, frequency domain performances, and so on, as well as how to design FIR filters using the Windows sync method. And it also shows you a basic implementation just in C without the CMSIS DSP libraries to get a basic understanding, so please do check those out beforehand. In terms of applications of FIR filters, make sure to check out video number 126 on my channel, which shows how to create a very basic impulse response loader to simulate, for example, the effects of a guitar cabinet and its frequency response, which we see plotted here, and also goes through a bit of the theory. Again, in this video, we'll be focusing on the CMSIS DSP libraries, and I'll show you how to import them and how to use the FIR filter in the CMSIS DSP libraries. As usual, a huge thank you to PCBWay for sponsoring this video. I had these digital guitar effects processor PCBs manufactured and assembled by PCBWay, and they did a fantastic job. For this, I used their PCB prototype service as well as their PCB assembly service. Make sure to check out their services, and I'll leave a link to them in the description box below. At the time of making this video, PCBWay also has their 10th anniversary, and they invite you to take the 10th anniversary tour, which you can on the PCBWay website. Again, I'll leave links in the description box below. Before we move over to actually using the CMSIS DSP libraries, we of course have to add the library files into our own project. I'll be using CMSIS version 4. Now there are of course more modern versions of CMSIS available, but I'm used to version 4, so that's what we'll be using in this video. And for that, I'm at their GitHub repository at github.com/armsoftware/CMSIS4. And I'll leave links to that in the description box as usual. We need to download two files from this repository. One is a .h header file, which we'll include, and one is a library file, which is a pre-compiled library with a specific DSP CMSIS functions. We'll navigate to CMSIS, then include, and what we want to download is this armmath.h header file. And if we go to the lib and then GCC, for example, we can see there are various different pre-compiled libraries here. And this depends on what core you're using, so M0, M3, M4, and so on. And we're using an M7 core because we're using the STM32 microcontroller in this case. Now, there are still 3 different libraries for the M7 core, and that depends what type of maths you're doing. So, for example, if you're doing floating point single precision, you'd use the FSP library, or if you want to use double precision with doubles, you'd use the FDP library, for example. We are going to be using the floating point single precision math library, so this is the one I'd suggest you download if you'd like to follow along with this video. Moving over to STM32 I've got my usual project open here, which we've seen in previous videos, which contains all the setups for the codec, processing, and so on, and we'd like to add the libraries to this project. The first thing I would do is in my project, go to the core include folder, and I'd paste in my arm_math.h header file there. And we also want to add in our library, our precompiled library. So for that, I typically right-click on my project, new folder, call that lib, And in that folder, I'll paste in the specific library I need for my ARM Cortex core. In this case, I'm using the single precision floating point math library. Now, because we placed alm_math.h in the core include folder, where there's no further linking to do here, but we do have to tell the compiler that it can find this precompiled library. To do that, go to Project, Properties, C++ Build, Settings, then go to the MCU GCC linker under Libraries. And what we want to do in the library search path, click on the Add, and then link, for example, to the workspace under your project into the lib folder. That's exactly what I've done here. We also want to link to the library itself. And for that, you simply click on that little plus button, the add plus on the top right, and type in the name of the .a file, but take away the .a and take away the lib at the start, so that it just reads ARM_cortex and then _math. That's all we have to do, then click apply and close. So now we're pretty much ready to implement the FIR filter with the help of these CMSIS DSP libraries, which are optimized for these Cortex microcontrollers, and we do get quite a bit of a speed boost compared to writing our own FIR filter implementation. To then see what we need to do to implement an FIR filter using the CMSIS DSP libraries, we'll go to the CMSIS DSP documentation. And this is something I definitely recommend you do if you're new to CMSIS and you want to find out how to use certain functions or what functions are even available. So in the CMSIS DSP documentation, I'll go on the left to reference, and then what we want to look for are the filtering functions. So open that up and we can see what filtering functions we have available here. In particular, for this video, we want to look at FIR or finite impulse response filters. So we'll open that section and we can see what functions are available to us. What we want are the floating point functions. So one we have here is the ARM FIR F32, which is actually the processing function, but we also need a second function for initialization, which is this ARM FIR init F32. You can see the arguments this takes here. Both of these functions require various arguments to be passed to them. If we click on more on one of these functions, we can see what the arguments are. For example, for the initialization function, it needs an FIR filter structure defined by the CMSIS libraries, how many filter coefficients or how many taps, what the kernel length is. We need to provide a filter coefficients buffer, so the actual coefficients and the actual kernel itself, a state buffer, as well as a block size number. Number of taps is fairly self-explanatory, it's the length of the filter. The coefficients are, of course, very self-explanatory as well, but we do need to look into the details. We can see here that pcoefs points to the array of filter coefficients stored in time-reversed order. And this is important we get right, otherwise, of course, our filter will not perform correctly. So we don't actually just simply pass in the kernel itself or the filter coefficients, but we have to time reverse the filter coefficients before passing them to this initialization function. Then another argument is pState, which is a state buffer. And we can see here, again in the details, pState points to the array of state variables, and pState is of length num taps plus the block size minus 1. And that leads us to the block size parameter. Block size is the number of input samples processed by each call to ARM FIR F32. And this also tells us something about this function, or this ARM FIR functionality, is that this is a block-based function. We can, of course, pass in one sample at a time, might be rather inefficient, so we'll pass in n number of samples at a time, which is quite good for us because in our audio DSP processing system, we are reading continuously via DMA from the ADCs certain block sizes, be that 64 samples, 128 or 256 samples. So we'll read in input samples via the DMA and ADCs and pass them as a block to the ARM FIR processing function. Initialization function we just call once we want to initialize our kernel and our FIR structure. Then the actual processing function is the ARM FIR F32. That takes in again the ARM FIR instance, the struct. Then the second argument is the actual input samples we want to process or perform the filtering on. Then the destination buffer, where the current output samples of this FIR processing will be placed. And then the block size, so how many input samples and thus output samples we have. So fairly self-explanatory. There are some quirks, for example, needing this temporary or intermediate buffer of a certain length, as well as needing the kernel to be time reversed. But other than that, it's actually quite a simple implementation. There are, of course, numerous ways of going about then implementing the CMSIS FIR filtering functions. I would just like to show you a simple method that is fairly generic, and of course you can adapt it to your needs. I've created a convolutiondirect.h and a convolutiondirect.c header and source file, and we'll go through the structs and functionality that reference the CMSIS DSP FIR functions as well. The first thing I do in the header file is include main.h because that is then needed for define with this FPU present define telling the CMSIS DSP libraries that a floating point unit is present for this floating point unit implementation. Then sometimes armmath_cm7 define is not there, and that's why I then want to define the armmath cm7 define, which tells the CMSIS libraries what core we're working with, and after that we can then finally include armmath.h. So there are some preliminary steps before including armmath.h that you should be aware of. Roaming back to the CMSIS functions, we have a filter kernel length, which is the number of taps or the length of our coefficient buffer. So I create a define of kernel length and a define of block length, which is our input block length. How many samples do we want to process every time we call the FIR process function? We'll come back to what these actual values should be, and this of course depends on your system that you're running on. Then I've just created a container, basically a struct, which includes the ARM FIR instance, which is the struct we need to pass to our CMSIS FIR functions. Then a floating point buffer, and this is this working buffer required for the CMSIS DSP libraries, as we just saw, and that has the length of kernel length plus the block length -1, as we just saw in the reference. Then I'm storing the kernel, but in a time-reversed order, and this is simply an array of length kernel length. Now, of course, you can pre-compute the kernel in a time-reversed fashion before you upload it to your code, and that's a far more memory-efficient thing to do. Here I'm just showing it for the sake of how you would time-reverse your kernel. The final floating point array is the output array, which is simply the block length we are working with. So if we have 64 input samples, we have 64 output samples every time we call the processing function. Then I have a link to an external constant float array, which is simply the test kernel we'll be using, or the test filter coefficients. Then I have two functions I've defined. One is the initialization function, and one is the update function. The initialization function will time reverse the kernel we pass to it and initialize this FIR processor, as we saw in the reference. And then we have the update function, which takes an input array, calls the CMSIS processing function for the FIR filter, and sets the output array. So fairly straightforward. This is simply massaged a bit and taken from the CMSIS DSP reference for the FIR filters. Now let's move over to the source file and let's look at the initialization function. This simply takes the container I've defined and takes in the kernel. And again, the kernel are the coefficients of our filter, or the taps in other words. Then I want to time reverse the kernel. So I'm simply looping through the entire kernel length and flipping the values in time, so that my last sample becomes my first sample, my second sample becomes my penultimate sample, and so on. I'm also applying, while I'm computing the kernel, some sort of kernel gain in case I want to change the overall amplitude of my filter kernel, of my FIR filter, and I've just defined that to be 1 for now, so there's not much happening there, but you can, for example here, adjust by adjusting all the amplitudes of the filter kernel, the overall gain of your filter. After that, after time reversing the kernel, all we have to do is call the ARM FIR init f32 function. So to that, we want to pass the struct, our FIR processor, which was simply the ARM FIR instance f32. That's the first argument. Then we want to pass the actual kernel length, so how many taps of this filter we have. Then we want to pass the time reversed kernel, this floating point array. Then we want to pass the working buffer, and remember the working buffer size has to be the kernel length plus the block length -1. Then we're passing the block length. And that's all we have to do to initialize and instantiate this FIR filter. So fairly straightforward, but keep in mind that the coefficients have to be in time reversed order, and that we have to create this working memory, the number of taps plus the block size -1. Then the actual update function is incredibly simple. All we're doing is calling the ARM FIR f32 function, which is this processing function. Again, simply taken from the reference manual. We pass this FIR processor, this ARM FIR instance f32 struct. We pass the current input buffer. That input buffer has to be a floating point array of the block length. Then we pass the destination, so where we want to put our output samples computed by the ARM FIR function. Then we pass the block length. So this ARM FIR f32 function is going to convolve our kernel with our input using these number of samples and placing this in the output array. And that's all there is to this implementation. In main.c, all I have to do is include the header file we just described, along with the source file, create one of these convolution or FIR filter structs. In int main, all I'm doing is calling my initialization function, which runs through the init function from the ARM FIR filter, so passing my struct as well as a kernel. And we'll look at how I've computed this kernel in just a second. So after initialization, every time I have my process function, so what I'm doing in this case is I'm actually double buffering, and this process half buffer function gets called by an interrupt after the DMA has filled in half of the ADC buffers. So every time we've required, let's say 128 samples from the ADC, this function is triggered, and then we do some block-based processing. What I want to do is convert my signed 24-bit integers, which are coming from the ADC, to floats. So I'm looping through these and filling in my input buffer with those samples. And then simply, I'm just doing a mono processing. I'm applying the processing using our update function, which essentially is just calling the ARM FIR F32 function, passing in my struct, which contains various buffers, the working memory, the output buffers, and passing in my array of input samples. Now you can see the length of this array is actually audio buffer size divided by 4. So the audio buffer size I've defined, for this case, just 256. There's a compromise between latency and how much processing we can get done. And I'm dividing that by 2 because I have a left input channel and right input channel, regardless if the system is mono or not, based on the I2S data. And I'm dividing it by 2 again. So in total, it's the audio buffer size divided by 4 because I'm doing double buffering. This process half buffer function is called every time half of the buffer is filled up by the DMA from the ADCs. So therefore, my actual block size is audio buffer size divided by 4, which is what we defined in the comdirect.h header file. Then after applying the processing on this block of samples, I need to convert these floats back to 24-bit output samples, and that's all I'm doing here before passing this to the output pointer, which is then used by the DMA to send information via I2S to the DACs. But essentially our main update function is very, very simple. We just have to pass it an input array of floating point variables of a given block size, which we initialize the FIR filter with. With all of that in place, let's see how we can actually compute the kernel for our FIR filter. There are many ways of computing the coefficients for an FIR filter. You could use the window sync method, as is the one method we explored in video number 17 on my channel, where I wrote my own program to compute the coefficients based on a window sync method. We could use optimization-based methods to find the right filter coefficients based on a certain frequency response we want. Or we could use tools such as MATLAB or Octave. They have also filter builders inside of them oftentimes. One of my favorite tools, if I don't have any particular constraints or I just want something quick, is T-Filter. And I'll leave a link to this in the description box below. And this is simply an online filter design tool. And I find it quite intuitive and quite useful because it spits out the coefficients in a C array quite quickly. The way you can do this, if you go to T-Filter, we have to type in our sampling frequency and the number of coefficients we desire. We can leave that as minimum, or we can set a specific amount of filter coefficients. Then we have to define pass bands and stop bands. The pass band and stop bands have to be from a certain frequency to a certain frequency, with a certain gain and with a certain ripple. So with just these basics here, let's click on Design Filter, and we can see it'll design a filter for us. So from 0 to 400 Hertz, it has a gain of approximately 1 with about 5 dB of ripple. Then we have this transition band between 400 and 500 Hertz, and from 500 Hertz to 1 kHz, which is half the sampling frequency in this case, we have an attenuation in the stop band with about 40 dB. On the right-hand side, on the top right, we can change this to C++ array, and this array is what we would copy over into our program and use as the kernel. And keep in mind, this isn't time reversed. So for our system, we have, of course, maybe different requirements. We certainly have a different sampling frequency. For audio, we will typically run at 44.1 kHz or 48 kHz or even higher. The actual sampling frequency I'm running at is 48,000 or 48 kHz. But due to my clock setup, my actual sampling frequency is 48.828 Hz, and I've written to define here, and that's what I'll copy in as the sampling frequency. So our Nyquist frequency, our upper limit of this filter, is going to be half that, so about 24.4 kHz. And then we can play around, add different stop bands, pass bands, and so on. So for example, if I want to have a pass band from 0 to 1 kHz, gain of 1, and a ripple of, let's say, 0.5 dB, and then I want to have a stop band from, let's say, 1500 to my Nyquist frequency with an attenuation of minus 60 dB, we can see the lines drawn here are essentially our targets. We can click Design Filter, and it's designed the filter for us. So pass band 0 to 1 kHz, we have this fairly sharp-ish transition band, and a stop band all the way to our Nyquist frequency from 1500 Hz. Then we can see the actual number of taps, or the filter coefficient length, the kernel length, is given at the bottom. And this is the number we would then use in our implementation as conv-direct kernel length. So depending on what filter length you have, the number of taps, the length of your kernel, they're all equivalent terms for the same thing, you would have to change your kernel length version here. Of course, it depends on how you implement it. For this very simple implementation, I'm just working with one kernel, but you could have maybe several different filters, and that is what is meant by this kernel length, so the length of the filter. The actual filter I would like to then show you implemented is this 683 length filter, which is incredibly arbitrary what I've designed here. All I wanted to show is that these FIR filters are quite good at segmenting up the frequency spectrum. So we can have very specific requirements on our FIR filter. For example, I've defined a stop band here that should be around minus 60 dB from 0 to about 1.8 kilohertz. Then I have a pass band with 0 dB of gain, maybe 0.5 dBs of ripple, then another stop band, then another pass band, maybe at 0.1 gain, so minus 20 dB, and then a stop band that's below minus 80 dB. So using this tool or using other tools, then you would input that information and get our kernel or our filter tapped out on the right-hand side. Now they are using double precision values here. We will be using single precision, so we will lose some accuracy in the actual implementation on the real world system. And this will pretty much always happen because we are working with floating points. We'll have some round off errors. We'll have some computation errors depending on how many taps we have. We'll have some discrepancies in the sampling frequency and more. But typically you can get very close to the theoretical performance of an FIR filter in the real world as well. Keep in mind, 683 taps can be considered quite a long FIR filter, so depending on what constraints you place on the design, for example, how much ripple you want in certain pass bands or what stop band attenuations you want, that may increase the actual number of taps or the length of the kernel of your filter. Now, depending on what processor you run this on, you'll have an upper limit, of course, of the filter length you have. Convolutions are quite computationally expensive, so the longer you make your filters, maybe your processor will have a hard time keeping up in real time. For the M7 microcontrollers, I found that I can actually run a 4096 point filter at 48 kilohertz with no problems, but higher than that, in real time, it does start to struggle. But do keep that in mind. Again, non-idealities will change the stop bands, pass bands, ripples, things you see, but you can get very close using these tools and you might have to tune them a tiny bit. The downside is, of course, of FIR filters that this is fixed, so we can't really change our filter coefficients on the fly like you can with IRR filters. But in any case, I'd copy over this array, and that's exactly what I've done, and I've copied that in a floating point array with that specific length. I know these are still double precision floating point values, but they will be truncated upon compilation, and of course we'll lose accuracy and precision, which will affect our FIR filter performance. But now let's upload this code to the board and see if our theoretical filter matches the real-world filter we see. In terms of setup, I have my input connected to a 1/4-inch jack and the output connected to a 1/4-inch jack to a Quantasylum QA403 audio analyzer, and with that we can analyze, for instance in this case, the frequency domain performance and a frequency domain plot. Connected to the STM32 microcontroller is also this tag connect probe, where I'm programming this device via serial debug. And I'm programming this using a J-Link by Sega. So thank you very much, Sega, for sending me one of those. I'll leave some links in the description box below in case you would like to check out these J-Link debug probes by Sega. After programming, I'm going to be using the QA403 audio analyzer. So the output is connected to the input of my DSP processor, and the input of the QA403 is connected to the output of my DSP processor. In this way, I can use the QA403 to create a frequency domain sweep, and I can measure the response at the output, and we can get an amplitude versus frequency plot. So now let's move over to the QA403 software. I have the software running. I'm using an FFT length of 512 kilosamples and averaging by 4, and I'm simply providing this exponential chirp at 0 dBV. So the way I've done that, simply on the left-hand side, selected generators, and I've got a dBV scale on the y-axis, and on the x-axis, it's a logarithmic scale. So with the pedal bypassed, as it should be, it's just a straight input to output connection, we simply have a flat frequency response. But now, with our filter implemented, and this is running the CMSIS DSP FIR function, I'll click toggle, and this is what we get on this plot. Now keep in mind, this is a logarithmic plot. So pulling this up next to each other, we can see the T-filter side actually has a linear plot on the x-axis, so I'll change my plot to linear. So this is what we now see on our pedal running the CMSIS FIR filter algorithm with our 683 long filter kernel. From about 0 to 2-ish kilohertz, we have an attenuation of more than minus 60 dB, so we're about minus 65 dB. Then we have this sharp transition band, we have our pass band, then another stop band around minus 60 dB, a pass band at about minus 20 dB, and then a stop band all the way to the Nyquist frequency of about minus 80 dB. Comparing that to our initial filter design, this looks pretty close. Initially, you have a stop band of less than minus 60 dB, a pass band, 0 gain, stop band minus 60, pass band minus 20 dB, and then less than minus 80 dB of stop band all the way to the Nyquist frequency. So these results are pretty good and fairly close to the filter we designed rather quickly. Keep in mind also the performance depends on the processing chain, so what ADCs and DACs you use. You might not be able to get this kind of dynamic range depending on the system, the bit depth, sampling rate and so on, and what processing you do, but this is rather close to what we designed for. Keep in mind, for example, this second passband here, we can see it's actually rolling off an amplitude with high frequency. If we zoom in, for example, on the first passband and let's look at the ripple, we can see the ripple, so the deviation from our target gain. It also decreases in amplitude, but keep in mind the scale is now 0 to -1 dB in this section where I'm hovering over with a cursor. So our actual ripple is still pretty good and limited to about 0.3 dB. And we can see here the first passband, the actual ripple that we've calculated seems to be about 0.3 dB, which is pretty close. Now, of course, we could do further tests where we actually pass time domain signals through this. Not particularly interesting. We get most of our information from this frequency domain plot, but be aware of in the time domain across certain frequencies, of course, you'll have attenuation or amplification, as well as time delays in your signal. So the processing will take some time, but also the filter itself will add in some time delays. But in any case, I hope this showed you how easily you can use the CMSIS DSP libraries to implement fairly lengthy FIR filters. Thank you very much for watching this video. I hope it was useful and I hope it showed you how easily you can implement FIR filters in your own designs and how easily you can actually design the filter coefficients using free tools on the web. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest hardware design, firmware design, DSP, and embedded systems videos. Thanks again for watching, and I hope to see you in the next video. Bye-bye.